All right, let's take a look at some applications of these derivative functions in this section. So we're going to look at a few different ones. We're going to look at some science applications, some business applications, and a few different ones in class tomorrow. Make sure your cell phone is put away and turned off and you're focused and taking good notes for the next few minutes. Have your graphing calculator out, maybe have Desmos pulled up, and let's take a look. We're going to start with a little science, a little physics application here. It says, suppose that the position in feet of an object moving horizontally at time t is given, in seconds by the way, is given by that position function. So S of t is our position. Graph the velocity function on the interval 0 to 5, and then answer the rest of the questions that follow here about that. Let's get the velocity function first. Remember that the velocity is equal to the derivative of the position function. So if this is my position function up here, my velocity is going to be 3t squared minus 27. We can graph that. That's a parabola that opens up and is shifted down 27 units. If you want to make a quick sketch on your paper here, we'll just kind of exaggerate the graph. We'll put negative 27 down here. And then it's going to open up like this. Be sure to label your graph. This is V, this is T. And we have an x-intercept over here and over here. I don't really care about the one, I say x-intercept, I should say t-intercept. I don't really care about the time that's negative. That's not relevant in the context. We're only going to work with positive time values. But this one I do need to determine, because the object is going to be stationary when it is stopped, when it has stopped moving. So that would be when the velocity equals 0, right? When you stop moving, your velocity is 0. So we want to know when the velocity equals 0 to figure out when the object is stationary. And to do that, I'm going to set the velocity function equal to 0. This is not too bad to solve. I'm going to add 27. And then divide by 3, so I have 9. So my t-intercepts would be plus and minus 3. And again, though, the negative I'm not concerned about, so the one that I care about over here is 3. So the object is going to be stationary at t equals 3. That's when the velocity is going to be 0, so that's when the particle is going to be stopped. Now, when is the particle moving to the left? So the particle is moving to the left whenever the velocity is negative. So make that note somewhere on your paper. The particle is moving to the left when the velocity is negative. So let's see, I'm going to write it up here. The particle moves left when the velocity is negative, and it moves right when the velocity is positive. So we're moving to the left on this interval right in here. And this would be from values for t between 0 and 3. So the particle is moving to the left on the interval from 0 to 3. Actually, I'm going to leave those open inequalities for now. And then when is the particle going to move to the right? That would be whenever the velocity is positive. So let's write that down. The particle moves right when the velocity is positive. So notice that the velocity is positive up here. It was negative down here, switches to positive up here, and that happens after t equals 3. So whenever t is greater than 3, our particle is going to be moving to the right. B says graph the acceleration function. So let's find the acceleration function first. Remember that the acceleration is equal to the derivative of the velocity. Don't forget PVA, that's going to come up a lot. So the derivative of velocity is going to be 6t. So that's just a linear function with a slope of 6 and a y-intercept of 0. So I'm going to go through the origin, go up 6 over 1, put a point. There is a very crude graph of my acceleration function. That's t, that's a. Make sure we label our axes. And it says determine the acceleration when the velocity is 0. So the velocity, remember, was equal to 0 at t equals 3. So the acceleration then at 3, to figure that out, I'm going to just substitute that into the acceleration function, and I get 18. The units for that would be feet, they said feet was our distance, right? So feet per second squared. Velocity would be feet per second. Acceleration would be feet per second squared. Now C says use a number line analysis to compare the signs of the velocity and the acceleration in the interval of interest from 0 to 5. So, all right, let's take a look at that. So I'm going to draw a number line here. So for the velocity, I'm going to put down the sign change for the velocity was at 3, if you'll recall. Notice to the left of the velocity, or left of 3 rather, the velocity we said was negative. To the right, we said it was positive. Acceleration, we're going to draw a number line for that, a different number line. Now, does the acceleration ever change signs? Well, it does at 0, but remember we're starting our interval at 0. So between 0 and 5, the acceleration, notice, is entirely positive over that entire interval. There's no sign changes for the acceleration. So here's what you need to know about the rest of this question. The particle is speeding up when the velocity and the acceleration have the same signs. They're both positive or both negative. The particle is slowing down when the velocity and the acceleration have opposite signs. So look at our number line analysis here, and when does that occur? Well, notice up until 0 to 3, the velocity is negative, but the acceleration was still positive. So on the interval 0 to 3, the particle would be slowing down because the signs are opposite. And then what happens from 3 to 5, notice that they are both positive, so that means the particle would be speeding up. And that's what we need to know to answer that question and how we use that number line analysis. Let's do one more quick example here. We're going to look at a business application. It says, suppose that the cost of producing X items is given by this function from 0 to 1,000. So we're only producing up to 1,000 items. Determine the average and the marginal cost. So marginal cost is the per item cost. So the cost to add one additional item to our production. And that is equal or defined as the derivative of that cost function. So I'm just going to take the derivative using our regular derivative rules, and I have negative 0.04x plus 50. And that's going to be our cost to add one additional item to our production level. The average cost, on the other hand, is if I take the total cost and I divide it by however many items are produced. So the total cost is the original cost function. So that's going to be C of x divided by x, which I've written down here. That's the original function, the negative 0.02x squared plus 50x plus 100, this function up here, divided by x. So that average cost does not involve the derivative at all. B says determine the average cost and the marginal cost for the first 100 items. So let's do each of those. The average cost, I'm going to go ahead and write, we'll call it A of x, that's fine. So A of 100 is going to be negative 0.02 times 100 squared plus 50 times 100 plus 100 divided by 100. And let me put that into my calculator. And I am getting 4,900 for the numerator divided by the 100. So that means on average, it's costing me $49 per item. So for the total cost, all my costs involved, on average, I'm spending about $49 per item. Now the marginal cost would be the derivative at 100. So that would be the derivative of 100, negative 0.04 times 100 plus 50. So let me put that into my calculator. And I am getting a value of $46. So what is the difference? This means that if I'm at 100 items, so in other words, if I have already produced 100 items, so at a production of 100 items, it will cost an additional, and again, I'm sorry I didn't leave you much room here, additional $46 to produce the next item. And we'll do a little more practice with this in class, so we'll go over this again. But that's what that marginal means, the cost to produce one additional item. Part C, it's the same, basically the same question. They're just using 900 instead of 100. So I'm going to skip that part for right now, but it's the same idea. You would calculate the average and plug in 900 for X. For the marginal cost, you would just plug in 900 to your marginal cost, your C prime function. D says sketch the tangent line to our cost function at those two locations. So what we're saying is at 100 would be down here somewhere. So this is the original cost function, C of X. And my derivative or my slope of my tangent line, maybe it would look something like this. And that would be my marginal cost. The slope would have been C prime at 100. And remember, previously we did calculate that. It was 46. At 900, now I didn't calculate that, but I'm gonna cheat a little bit and use Desmos to get the marginal cost at 900. Let me go back to Desmos here and show you that real quick. So if I put in C of X, the original function was negative 0.02 x squared plus 50x plus 100. And then Desmos will do C prime at 900. I'm getting 14. Look at that, big difference. C prime, remember when we did it originally at 100, we had 46, right? Here it is at 900, it's only 14. So on my graph at 900, if we were to graph the tangent line, the equation of the tangent line, or the tangent line function rather, it would look something maybe like this. I'll try to draw it as smooth as I can. And make a note here that C prime at 900 from Desmos was 14. So here that means our slope at 900 would be 14. Does that coincide? Yes, I would say so. You can see that this first one is much, much steeper than the second one. So that means the cost to produce one more item at production level of 900 is only $14. So you can see costs have dropped is basically what we're saying. As we produce more items, our costs go down, which we find often happens in the real world. If you've ever ordered t-shirts or something like that, the more you order, the cost per shirt tends to go down. That's what we're talking about, the cost per item to produce one more item. And you can see it dropped considerably from 100 items production to 900 items production. And if you're a business major, this is a really important idea. This will come up a lot. Even if you're not, even if you're a science major, at some point you'll be looking at costs and things like that. So we'll do a little bit more practice with this in class tomorrow.